everybody! How's everybody doing? Absolutely fantastic today. Good to hear, good to see everybody here today for some Math 126. How's everybody tonight? Type that up. How's everybody tonight? Hopefully you're doing well. Hopefully everybody out there watching this is doing absolutely fantastic. All right, we are here. We're doing good things. Emma, hello. Good evening. How are you doing? How are we doing today? Doing great. I'm doing fantastic. Good for you to come on by the stream. Thank you very much. Maybe, I don't know, maybe just you and me today, Emma. Don't know. So, the first one to show up, and I'm like, all right. A little bit past that 6 o'clock, but hey, I'm glad you could still make it out regardless. So, won't be unprecedented, but you know, still have a nice time regardless. Oh, there we go. We got number 2. We got Lee Wen. Hello, Lee Wen. How we doing? Hopefully doing fan-diggy-antastic. Hopefully both of you are doing very well this evening. Good. I'm doing great. Doing great. We're having a grand old time today. Let me tell you, it is new material to do, but fortunately, this shouldn't be all that bad. I think this stuff's gonna be actually rather simple. At least this stuff, to be honest. So, we're on a pretty decent pace here. So there's a few parts I'll need to catch up on, but we're on a pretty decent pace so far. So far, so bueno. Any Emma, Lee Wen, you guys any plans for tonight after we're done here? Are we just gonna do the usual? Just kind of eat some dinner, rest up. Maybe go to Taco Bell. I don't know. Hey, Connor! Hey, long time no see, my friend. How are you? Good evening to you. Do homework. Man, that's productive right there. I can't argue with that. Do more homework. My homework assignments aren't that long. They take a little time, but I've figured that we've been doing the homework together here. I figured they would go by a little bit more smoothly than what they did before. Connor, my dude, how you been? Long time no hear. Hope you've been doing well, my friend. Hopefully you've been doing hopefully it's been chill. Hopefully you've been having an absolutely fantastic time out in Ireland. Had a football match in 23°C weather. Oof, that's pretty hot out there. Watched the boy Toby. Oh yeah, how does the boy Toby fare today? Was today like the second episode? Is it like an everyday thing? I don't know if Love Island's a weekly thing or an everyday thing. Every day? Okay. Yeah, how did Toby do today? He had a date. Oh, okay. So I read a synopsis and it said he had a date. He had paired up with what's that girl's name? Kaz. That was her name. Yeah. So our boy Toby having a date with maybe Kaz. Is that who he went on a date with? Yeah, let's hope he gets lucky in love. That would be really nice for him. He's a good guy. That show's got to be incredibly popular. I mean, I don't know. At the very least, he has exposure and stuff, so. I must say. All right, waiting on maybe a couple more people. We'll wait another minute or two. Maybe we'll get Elizabeth in here. Maybe we get Nick in here if Nick's gonna show up today or not. Maybe Nick's a little busy today though. Nick did mention that. So, all right. Oh, I'm here. Okay, I'm just listening. Okay. Well, I don't know. You don't say nothing. I'm like, I want to. No, I know there's like a. I know there's like a, hey, there's only like a few people who attend the live lectures, but I'm like, hey, I always like to build a rapport. Always important. Yeah, they got back and says it's the best picnic he has been on. So all the lads kind of looked at him and says, "Is that the?" All the lads looked at him and said, "Is that the first picnic?" Poor Toby. Poor Toby. You know what? Toby's like a super innocent guy. He's got that innocence about him. Yeah, maybe the other guys have experience, but you know what? Some ladies like innocent lads like Toby. Maybe that's part of his charm, you know? I gotta respect that. So the other guys are like, I got the moves. He'd be like, Toby's like, I don't got no moves. I'm just Toby. All right, ladies and gentlemen, let's do this. Let's do some intros here. Stop. Talk about Love Island some other time, I suppose. All right, let's do some intros. Let's get going here. Again, if the music's too loud, just let me know. I'll turn it down, and we'll be all right. All right. Okay, let's get started today. Welcome back to Wednesday. All right, so we're going to pick up where we left off last time. We talked about exponential functions, and we also talked about the beginnings of logarithmic functions. We took a look at how to use the some rules there. We took a look at the power rule, the quotient rule, the product rule. We looked at all those guys. Well, at least if I watch it for the first time, it may take me away from football. Not know. Yeah, I understand. Alright, so today we're going to switch gears here with logarithmic functions. We're going to look at something else here, specifically. Alright. Okay, so what we're going to do here specifically for today is we are going to look at more about logarithmic functions, but the last thing that we did do here, besides, of course, answer questions regarding logarithms and how to split them up, and how to expand them or compress them together, is we need to look at some other log rules here. Actually, I should probably take these away elsewhere. Actually, I'll put them. Alright. Alright, in any case, let's go ahead and talk about what is the graph of a logarithmic function. So just like what you see here, like the log of 1/4 x, or what would a log function specifically look at? Have a good one, Connor. You take care of yourself. All right, so let's look at a particular function here, and we'll look at a basic logarithmic function, and we'll do it out, and we'll see some properties and characteristics that we can actually automatically get from a graph of a basic logarithmic function. All right, so let's look at the function here specifically of f of x equals log base 2 of x. Okay. Now, one of the things we talked about here last time is, okay, we could rewrite this as y is equal to log base 2 of x. This is something that we can certainly do here with that. Now, what we can do after that is basically, the issue that I have here is that I can't write this as a exponential. I can write this as an exponential function, but I can't really do this on a calculator like directly. I can't do like log base 2 of x on a calculator unless you have like the Inspire. Inspire can do this, but if you have like an 83, 84, you can't do log base 2 on your calculator. Instead, you need to rewrite it in terms of an exponential function. Okay, so let's go ahead and remind ourselves what we did yesterday. How can I translate? So I'm just going to scroll up here for a moment. How can I translate y is equal to log base 2 of x? I'm going to use this translation here between logarithmic and exponential. How can I translate y is equal to log base 2 of x? How can I set that up? I want to put it in exponential form. How do I put this in exponential form? Y is equal to log base 2 of x. What do you think? Emma, Lee, Wen, or Elizabeth? What do you guys think? What's that going to look like? This is kind of important because we want to be able to put... Well, that's b to the y equals x is correct, but I need the numbers here now. I have log base 2 of x here, Emma. So 2 to the y is equal to x. Okay, that is correct. So with the base 2, again, that b is now 2. So we have 2 to the y here is equal to x. All right? Because now we actually have a base b here, that being the number 2. Now we're just going to map this out. Okay, we're not going to do anything too fancy going on here. But the one thing that we have to recognize about this is 2 to the y being the correct translation is, if you notice here, normally what we do in regular functions is we plug in an x value and get something back out for y. In this instance, well, you have 2 to the y is equal to x. So basically it kind of goes backwards. We actually have to plug in a value in for y and get something back out for x because of the way that the function is written after it's translated over. So let's go over and then we'll get subsequent points based off of this, of course. So, can anybody tell me here, what is, if I plug in y is equal to 0 here, what do I get for x? What do I get for x here if I plug in y is equal to 0? All right, 1. That's correct. Nice, nice. Okay, good stuff. So far, so good, ladies. All right. All right. Let's try 1 for y. If I plug in 1 in for y, what do I get for x? Two. Okay, that's correct. Very good. Let's go ahead and put in some other numbers here. Why not? Let's try, well, let's try 2. If I plug in 2, what do I get? So 2 to the second power here is 4. Okay. And how about minus 1? What do I get for minus 1 here? All right. We have 2 to the minus 1. What's that? Or should be a little bit further up. 1/2. That's correct. Remember, 2 to the minus 1 power equals 1 over 2 to the first, which equals 1/2. And then here we have, let's try minus 2. About minus 2. One fourth. Okay, good. That's right. Again, 1/4 here, you have 2 to the minus 2 is equal to 1 over 2 squared, which is equal to 1/4. Okay, now, we can make a general graph based off of this. It's not a very hard graph to make. Let's make a generic graph here based on this log. So here we got 1, 0, right about here. 2, 1, right about here. 4, 2, right about here. I'll scroll this up a bit. 1/2, minus 1, so right about here-ish. And 1/4, minus 2, so right about here-ish. So we connect these dots here, what a log graph generically looks like, okay, for basic log graphs, mind you. All right, so here's what a log graph will look like, just like so, okay? So this is your generic basic log graph, all right? So there are characteristics or properties, whichever way you want to call it, associated with these log functions here. And you can get them based on the picture that you see up here on the screen here. So first and foremost here, for logarithmic functions, we can say here that domain here is equal to 0, infinity. So if you notice here, we do have a domain here. Again, this links to the fact that we have a vertical asymptote at x is equal to 0. So again, we have a vertical asymptote instead of a horizontal asymptote from last time at x is equal to 0. So again, the asymptote there, the imaginary line that you get really, really close to, but don't quite touch. The range here is all real numbers. Okay, so every number is what we get here. Again, basically at the end of the day, this is just a flip of the domain and range of exponential function. That's essentially what it comes down to. Even the points are flipped. So instead of 0, 1, you get 1, 0. Instead of 1, b, for exponentials, you get b, 1. Again, because you're going backwards. Instead of negative 1, 1 over b, you get 1 over b, negative 1. And all transformation rules apply once again. Okay, and these are for just basic, again, basic logarithmic functions, okay? Again, when you transform, move stuff up, down, left, right, of course, that stuff is going to change naturally. Okay. All right, so if we go back to our question here, all right, now that we have a good idea about what a graph of a logarithmic function looks like, all right, so it looks exactly, again, the basic graph looks what you see here on the screen. Let's go to our homework question. Okay, and so it asks us, okay, sketch the graph of log of 1/4 of x. Okay, so which one of these graphs would be 1/4 of x? Would it be the first one, the second one, the third one, or the last one? I'll actually make this smaller to see all 4 of them. Which one of them would it be? Would it be the first, that over? Be helpful if you could see all 4 of them. There we go. So it'd be the first one, the second one, the third one, or the fourth one. Which one would you think would be your winner? Second one? Okay. So let's pick the second one here. See if we get our results. Okay. We can automatically the third one? You think the third one is the correct answer? Okay. Well, we got the second one or we have the third one. Now, obviously, we can remove the first and fourth ones because we don't have a domain that's negative, so you can throw those right away. All right. Let's take a gander here about 1/4. Now, 1/4 is an unusual number because 1/4 is a fraction, okay? And because I mentioned here that transformation rules apply, again, 1/4 would work the same way here as if you had 1/4 to the y is equal to x. So if you think about, again, having an xy chart here, you plug in 0, you would get 1. All right, so that number there is pretty standard. As you can see there, both of them have that number. 1, you would get 1/4, so you'd have 1/4, 1. for that. All right, so that's what you would have for that one there. So let's see, 2 you would have 1/16 and so on and so forth. Okay, well let's check to see which one is going to be our winner here. The 1/4 would be 1. Okay, now in this case here, it is going to be slightly a bit different. So 1/4 would be like right about, I don't know, like here. And we'd have 1, which is like right about here. So again, you just have to be a little bit careful about transformations. Oh, here they come. Second, folks. I get these bots. Get rid of the bots. Goodbye, bots. Have a great one. All right. I love bots. They're so terrible. All right. Sorry about that. All right. So in fact, in this case here, because 1/4 is a transformation, does it look like this? Well, we would have a point of 1/4 comma 1. So 1/4 comma 1 here would be somewhere around here. And in this graph here, 1/4 comma 1 is not down here, it's actually up here. So in fact, it will be the third one here in this particular case. Again, strictly because 1/4 is a fraction and it affects the transformation. So 1/4 affects transformation of the basic graph. That's going to put that there. So if we check that one should be correct, would be actually the third one here. All right. Are there any questions about that? Not for this one, because the calculator can't do 1/4 to the y power. So you're a little confused about how it's the third one and not the second one. So, okay. So let me go back here for just a moment, okay? This is the basic graph that we have here for, most log functions. But one of the properties of log functions here, Elizabeth, is that if we have any other numbers, that affects the transformation of the graph, meaning we can shift it up, down, left, right, we can flip it over, we can do anything that we want here when it comes to doing those types of graphs. Okay, and when we have a fraction specifically, in effect, it flips that graph over on the x-axis. So you can actually see what happens here when you have a fraction here. It actually, when it goes ahead and actually reflects it on the x-axis, because to select that here again, let me go over this one more time. Just do a little XY chart if you're not fully convinced, and just map out points that are going to appear at 1/4 to the y power is equal to x. Well, you'll always get the point 0 and 1 comma 0. That's already given. You'll get 1/4 comma 1. If you chose 2, you'd get 1/16. However, if you chose negative values, if you chose -1, there's where you get your positive 4 from. If you chose -2, you'd get, you get positive 16. Things change when you have a fraction here. That's why everything kind of flips over in this case. And that's because of the property of it being a fraction. Okay. So if you're not fully convinced, write out an XY chart and then match those points there appropriately with the graph that's given, and you're going to get your final result there, Elizabeth. Okay. So strictly that comes from transformations by itself. I hope that made sense there, Elizabeth. If you have any other questions, just let me know now. So I can clarify a little bit more. Okay, okay, cool. Okay. Okay, next. Let's talk about what we're going to be doing here next. We're doing a couple of these next next to these problems here. All right, and so we need to use logarithms to solve for, in this case, for like 7, 8, and 9. For 7, 8, or 9 here, we need to solve for t in any one of those three particular problems. Now, I'm gonna let you pick for me here which problem you would like me to do. Would you like me to do 7, 8, or 9? Which one would you like me to do? Would you like me to do 7, 8, or 9? All right, so let's go ahead and do 9. All right, let's go ahead and see how we can solve for t in that case. But we're going to need some tools to help ourselves out with that. All right. You guys like the tough ones. Like, do this for me. I'm like, all right, we'll do it. All right, that's fair. All right, so we have 4e to the minus 0.8 to the t power is equal to 10. Okay. So here's our problem right here. Our goal is to go ahead and solve for t. Now, in order for us to solve for t, well, we need to get t by itself. That's the whole goal. Well, let's get rid of the ugliest part here first. The ugliest part, regardless of which way you slice it, is this denominator 1 plus 4e to the minus 0.8t. That looks pretty disgusting. All right, so we don't want that there. We want to get rid of that guy. So what we're going to do is we're going to multiply by that on both sides. So that's what we're going to do here. We're going to multiply by 1 plus 4e to the minus 0.8t on both sides. Cancel that out. Okay, so let me show you what's going to happen here. We have 20 on the left-hand side. On the right-hand side, I'm going to distribute this 10 here to both of these terms. I'm going to have 10 plus 40 e to the minus 0.8t. Okay. So we're fine there. We're working our way forward to solving for t. Okay. Now, again, we still haven't gotten t by itself, but we're getting fairly close to that point. Next thing that we're going to do here is we're going to go ahead and subtract by 10 on both sides. Let's do that next. Again, getting rid of our roadblocks and just trying to get t on its own is the goal. So notice I'm just taking the same algebraic approach that I normally would in like regular algebra problems. I'm not doing anything super fancy just yet. I will be doing something super fancy here momentarily, but still working our way through fine. Let's do the next one here. We have 40. So we'll divide by 40 on both sides. Okay. So we get 10 over 40, which is 1/4, equals e to the minus 0.8t. Now, it's at this stage here, like everything I've done up to this point is pretty much standard fare for what you do for normal algebra stuff. You know, moving stuff to one side, dividing on both sides. Okay. Now that's all well and good. But now we need to be a little bit fancy here about how to get t by itself at this juncture. Now, in order for us to do that here, we're going to use one very, very important property here of logarithms. And I need to bring up the notes for that. So let me bring that up. And that is this, is that we have additional properties for logs. So again, if we're going to solve problems involving logarithms, use properties and rules in order to solve problems for logs and e. So I put several of them down here. For example, if you have log base b of 1, that's 0. Log base b of b is equal to 1. This also applies to natural logs, which is one of the easiest things to use and exploit in order to solve for problems like these. So if you notice here, for example, natural log of e to the x is equal to x. This is this is a pretty big deal here, okay? Also, another way you can actually look at it this way is, again, using the power rule that we discussed here yesterday. You can also use that as well. But in order to use the power rule, we have to take the natural log of both sides. So that's the real trick behind these problems, is that I want to be able to use these properties, but I can't use it in its current form. But the trick is that, okay, let's put here. The trick is to take the natural log of both sides. Okay, that's going to be very, very important. We take the natural log of both sides. Now we have access to all the rules, the product quotient, and especially the power rule. And then these rules, these additional log properties that you see here on the handout, you can go ahead and use those as well. All right, so let's see what happens when we go ahead and do that. I take the natural log of 1/4, and I take the natural log of e to the minus 0.8t. Now, basically, here's how it works with like natural log and e. The easiest way to kind of look at this and kind of view it is what I like to say is the crude way of doing it, but it's effective. In effect, natural log and e effectively kind of cancel each other out. Okay, so if you look at it like that, it becomes a little bit easier to understand. So essentially, natural log and e cancel each other out and just leaves you with the exponent that's over in that side. Again, you could use a power rule to justify it as well, but it's the same exact thing. You get negative 0.8t here. On the left-hand side, we haven't done anything, so that's still going to be natural log of 1/4. Okay, so we haven't touched the left-hand side. It's the right-hand side we cleaned up a bit. Now we just do it like regular algebra, and we divide by negative 0.8. And then this is what we're going to enter into our calculator to find out what our answer for t is. So let's go ahead and take a gander, see what we get. Well, let's bust out the calculator here. We'll show you how to get natural log and e's and all that jazz. So okay, so we're going to take the natural log. Now the natural log key is next to the number 4 key on your calculator here. And again, it'll say natural log. It'll have a set of parentheses next to it. Make sure you keep those parentheses because you're going to put in 1/4. Close those parentheses. Then we're going to divide that by negative 0.8. All right. Go ahead and enter. And here we get 1.7329. All right. We're going to 4 decimal places. I don't know how many decimal places they want me to do, but let's go ahead and take a look at the homework problem. Let's see how many decimal places they want us to do. They want us to do 2 decimal places. Okay, so 2 decimal places. We're just going to get 1.73 as our answer here. And we'll check it out. See what we get. And where is it? There it is. Okay, that's the correct answer. Good. All right. Good stuff. Any questions about number 9? No? Okay. Alrighty. Hopefully that was pretty straightforward. Alright, now those other problems are pretty similar. Alright, so the next problem I want to do one more problem here from this section. Now the last 3 questions are pretty similar to what we just talked about here. Again, just exploiting the rules here and just kind of moving stuff around. The last question I want to do here is either question number 10 or question number 11. So I'll let you guys pick here between 10 and 11. Which one would you like me to do? Like me to do question 10 or question 11? Number 10 or number 11? I'll do that as the last example here for this particular section. Alright, Emma says 11. Let's see what Lee Wen and Elizabeth have to say. Alright, Elizabeth also says 11. Okay. Go ahead and do number 11. Let's take a gander at that one. Let's see what we're working with. Why not? Alright. Shrink this down to half a screen. No. Like half a screen. Yep. Half a screen. Alright. Number 11. Blood pressure. Alright. Alright. Okay, so a normal child's systolic blood pressure may be approximated by the function P of x is equal to m times natural log of x plus b, where P of x is measured in millimeters of mercury, x is measured in pounds, and m and b are constants. Okay, given that m is 19.4 and b is 18, determine the systolic blood pressure of a child who weighs 83 pounds. Round your answer to the nearest decimal point. Okay, so let's at least, first and foremost here, any type of word problem, let's just organize our stuff here. And then once we organize our stuff, let's put those numbers in the right places according to the formula that they gave us, so at least we can see exactly what we're working with. So here in this instance, let's go ahead and see here, we are given a few things here. We're given m here, which is 19.4. We're given a b here, which is 18. And specifically here, x is measured in pounds according to the problem here. And we're given a specific child here who weighs 83 pounds. Okay, so x here is going to equal 83. Okay, so all we're going to do here is plug in m and x and b into our function. And just going to see what we get. We're going to get. So we're going to get 19.4. That's the m. Times natural log of x, which is 83. Plus b, which is 18. Okay, so let's see what we get here based on how many millimeters of mercury we have here. Right? 19.4, natural log of 83, plus 18. So here we get 103.73. Right? So is it one decimal place or two? Oh, one. Okay. For some reason I thought it was two. No, I'm still putting two. All right. Let's check it out. Did we get it right? The answer is yes, we got it right. Very good. All right. Any questions about that? I know the last three problems are very similar to the previous example of just manipulation, so just got to put those numbers in the right places. So, all right. So that, in a sense, is the end of section 5.2. All right, so that's done and dusted. All right, however, I am going to point out here very specifically that the things we just talked about here in 5.2, especially using the log properties here, are going to be used throughout the course of the rest of this chapter. Okay, so going back to these guys here for just a minute, these little properties here are going to be fairly useful for what we want to be doing here in the rest of the chapter. So I'm just going to point that out here for what we're specifically doing. Now, also as a side note here, although nothing related to this section, by the way, but is related to the chapter, the next section here is going to be section 5.4. Okay, we are skipping section 5.3. There is no homework associated with section 5.3. There will be no test questions associated with 5.3. Remember that anything I do not cover will never be on an exam or the final. Okay, so just pointing that out there. And don't be surprised that there's no 5.3, as purely intentional. Okay? All right. So let's move on to section 5.4, and let's take a look at the question there revolving around that guy. So section 5.4 deals with our friend E. And it talks specifically about the derivative of e to the x. All right, so we're going to look at the derivative of e to the x. We're going to see how we can work with e to the x. Okay, we're going to see several questions, of course, revolve around that. So let's go ahead and see what we're working with. Close this one out. Open this one. Okay. So again, just think about a lot of the things that we just talked about here in this last section. We're going to be just doing it again. Okay. Now, in order for us to understand this here, again, because we can apply the derivative here of now e to the x now that we've formally introduced it, the derivative of e to the x is exactly equal to e to the x. No, I'm not joking here. The derivative of e to the x is exactly the same thing once again. Okay, you just get right back where you started for the derivative of e to the x. However, if there is a function in place of that exponent for x in e to the x, then you will have to do the chain rule for that. Okay, so going back to our chain rule that we talked about here in the previous chapter, if we take the derivative here of e to the f of x, which is just some random function, we keep e to the f of x, keep it the same. E would be our outside in this case. And then multiply by the derivative of the exponent, which would be the inside here of that function. Okay. So I'm just going to point that out here for just a moment. All right. Okay, now, I want you to look at the very first question here from section 5.4. All right, I'm not even going to write this one down specifically. You could do the others, that's fine. But this one here, question number 1. What is the derivative of 6e to the x? What is that derivative? Anyone of you ladies tell me what's the derivative of 6e to the x? What do you think it is? Derivative of 6e to the x. If you already know what the derivative of e to the x is, which is e to the x, we have a 6e to the x here. What's our answer for that? All right. Now I agree with one of those answers. I'm going to go ahead and put it down here. The answer here is going to be 6 e to the x. That's it. It's the same exact thing. So in this case here, Lee Wen, we're not using the power rule in that regard where we're subtracting by 1. And that's because, again, the derivative here, the rule here is that e to the x just gets you back e to the x. The 6 effectively doesn't do anything. It's just pretty much the same. It's just hanging out. But 6 e to the x, you get the same thing back. That's it. Just that simple. So we're not subtracting 1 from our exponents. We're not doing anything like that. And just leaving it alone because that's what it is. All right. Again, I can submit this and I can show you here. And you see that's correct. Okay. Well, maybe you guys can get this next one. Let's see if you guys get it. Let's see if you ladies get this next one here. We have e to the negative 6x. E to the negative 6x. I'll write this out if you want me to. I don't have a problem with that. That's okay. Oh, that's okay, Nick. We are on section 5.4 now, Nick. We did the first part there. So my recommendation there, Nick, is just to rewatch that first half there. But we're just starting section 5.4 right now. So we're on the last question of that handout, by the way. So we are skipping section 5.3 here. So I'm just going to let you know there, Nick, okay? So don't want you to be surprised of not doing section 5.3. There'll be no test questions, no nothing with 5.3. It's omitted. Okay, you guys think, what is the derivative of e to the minus 6x? What's that going to be? What do you think, guys? Oh. To the minus 6x. Let's write it down. Let's write it down. Maybe it's a little confusing, but let's write it down. So this is our function. We want to find the derivative here. Now, if we're using the rule here appropriately, then basically the derivative is we keep e to the same function. We keep the function the same. We're just going to keep e to that minus 6x. That's going to be the same. So if you notice here, I got that. And, okay, Emma's got minus 6 e to the minus 6x. And that is correct. Good. That's right. So we keep the same thing here as our exponent, and then multiply by the derivative of our exponent. And the derivative of minus 6x is just minus 6. So that's correct. Minus 6 e to the minus 6x. I swear, don't make it super complicated on yourself. It's that easy, okay? Keep the exponent the same, then take the derivative, multiply by the derivative of the exponent. So it's just the same concept for like chain rule, outside, inside, okay? Same exact rule. So if we try it out here from the homework. All right, and we'll go ahead and submit that out. And that is correct. Good. Okay. How about, okay, let's look at this next one here. I'm going to do number 4 here. Again, a different look, but again, an important one nonetheless. X over e to the x. Let's figure out that derivative. Now, I will give you a hint for this one. The hint for this one here is remembering how to rewrite this problem before you try it. Okay, so that's your big hint. Your big hint is to rewrite it first before you try it out. Or you can do the quotient rule either way. What would that look like here? Would you like to do the quotient rule or rewrite it? Both are effective answers, by the way, so one's a little bit more confusing than the other, but either way. No, you want to do it both ways? Is that the vote? If I'm to understand you correctly, Elizabeth, would you like to do it both ways, or do you want to do it one way? Just see which way makes okay. So, all right, let's do it one way. What I perceive to be the easier way, but again, it depends from person to person. If I were to rewrite x over e to the x, now this is a question you guys have to answer from me here first. How can I rewrite this? How can I rewrite this problem here? How can I rewrite x over e to the x? I need you guys to recognize this part here. So I think it's easier if I do it this way for one reason. So that's close. You kind of have it a little bit backwards there. You have x e to the minus x. Okay, so you kind of have that backwards here. Again, it's like if you have 1 over 2 to the first, that's equal 2 to the minus 1, right? You still keep the base the same, but the exponent is the only thing that changes from a positive to a negative. Okay? So it's the same exact thing. The exponent stays the same, but again, the base stays the same, but the exponent changes from positive to negative. All right? Does that make sense there? Are there any questions about that before I move forward? Any questions, Lee Wen, Emma, Nick, about that? Okay. Well, I'll move forward then if there are no questions. All right. So the next thing that we're going to do is we're going to do the product rule here. Okay. So again, you can assume that we have f here as x and g here being e to the minus x. I haven't gotten to the final answer there yet, Emma. I'm working my way toward there. I haven't quite made my way there yet. All right, so the product rule, anybody remember the product rule? What was the... Oh, no, that's okay, Emma. Don't worry about it. What was the product rule again? Yeah, I'm just trying to rewrite the problem here. I haven't made it to the final part here. So, what is the product rule? Anybody remember? What was the product rule again? F prime g plus g? Well, don't forget, Lee Wen, we got f prime g plus g prime f. Okay, so remember that's the product rule there. F prime g plus g prime f. There we go. Very nice. That is correct. So let's go ahead and find our f prime and g prime here. So our f prime here is going to be 1. That's the derivative of x. Fine. Let's take a look at the derivative of g, which is e to the minus x. Now, e to the minus x basically is you keep e to the x the same, e to the minus x, you keep that the same, and you take the derivative of minus x, which is minus 1. So in reality, you have minus e to the minus x. Okay, if you were to clean that up just a little bit. All right? So that's g prime. So if we put that together here specifically, we have f prime, which is 1, times g, which is e to the minus x. Here we have plus g prime, which is negative e to the minus x, times x. That's f. And there we go. That will be your answer here. We can clean this up a little bit, actually. So let's do a little cleanup. 1 doesn't do anything. Get e to the minus x, and here we get minus e to the minus x. You could take this a step further, as many steps as you. Actually, let's write it. And you know what? No, keep it that way. There you go. Okay. You could write it as minus x e to the minus x, whichever way you want. It doesn't really matter. So I'll write it like this. We have e to the minus x e to the minus x. Okay. Want to write it like that, you can. It's the same thing. All right. If we plop it out, let's see what we get. And we got it. Now, that's one way of doing this problem. The second way of doing this problem is to use the quotient rule. So you're like, maybe I don't want to do it that way. I want to use the quotient rule. And with the quotient rule, you're going to end up with the same answer. It's just may not going to look like what you see here. So using the quotient rule, you have x over e to the x. You have f and g. Remember, the quotient rule is f prime g minus g prime f over g squared. Okay, so here we have f is going to be 1, and g here, the derivative of e to the x is just exactly what you started with, e to the x. You have f prime, which is 1, times g, which is e to the x, minus g prime, which is e to the x, times f, which is x, all divided by e to the x quantity squared. Okay, so basically my point of contention is that this right here, this guy, is the same. Oh, I didn't like when I did that. This guy here, let's do it that way. This guy right here is the same exact thing as this guy. Okay, there's no difference between those two. And I know that looks very different in terms of the terms that are written, but again, this is a little bit more simplified than this version right here, so that's why it looks different. So if we clean it up just a little bit, it looks fairly similar, not exactly. But in reality, that's exactly what it is. Okay? So this would be an acceptable answer as well. All right. Questions about that? Sometimes the reason why I find this to be a little bit more complicated, because as you can see there, knowing that these two are equal to each other is kind of difficult to see sometimes. So hence why I point out sometimes doing the product rule, maybe a bit easier to do. It's all in one line. Okay. All right. Shall we take a break or keep going? It is 7 o'clock, so I'm going to leave it up to you. Do you guys want to take a break or do you want to keep going? Keep going? Okay. We keep going with a few more examples, of course. All right. We will keep on trucking. Let's do it. Okay. Let's see. Which one do you want to do? We're definitely doing number 10, so that part's not a problem. But, which one do you want to do? We have 6 through 9. Yeah, we'll do number 10 for sure, but you guys pick, I go with democracy, Elizabeth. I just go with democracy. So 6, 7, 8, or 9. You guys pick 'em. Which one would you like me to do? Not picky? Okay. 6, 7, 8, or 9. Which one would you like me to do? All right, Elizabeth says 6. Again, you get pick them 1. 6 or 9. Okay. 9. 9. Okay, let's do 9. Okay, so the way we want to go ahead and do number 9, not too bad. One here is actually more straightforward than you think. Okay, let's do it. Okay, so write down the problem here at least. We have f of t equals 3e to the minus 2t minus 3e to the minus t. Okay, so we're just going to take these as two separate guys. If we're going to try and find this derivative here, we're just going to first, remember, the 3 just kind of sits there. It just kind of flops around. It sits there. It doesn't do anything. Now, e to the minus 2t, we're going to do the chain rule on that. Again, that's going to be e to the minus 2t, because we don't change the exponent. And then we take the derivative to the exponent of minus 2t, which is minus 2. We want to repeat this process here for the second term as well. So we keep the 3 here, doesn't do anything, keep e to the minus t, but then what we go ahead and do is take the derivative of minus t, which is minus 1. Now let's clean this up. Let's see what we get. We get 3 times minus 2 is minus 6, e to the minus 2t. Negative 3 times negative 1 is plus 3, e to the minus t. And that is your final answer for number 9. All right. It's that easy. I know you guys were looking for something more crazy, but that's it. All right. Questions about that? Hopefully that's not too shabby. No? All right. Okay. Now the next one I want to do here. Oh, yeah, sorry. I'm being a little too fast there. Sorry. Need to stop and make sure you guys are all squared away. Sorry. Okay. Let's go to question number 10. Now that's the tougher of the two questions, but the process here will be pretty much the same as we've done before. Question 10 says, find the equation of a tangent line to the graph of y equals e to the minus x squared at the point 3, comma 1 over e to the 9th. Okay. So in this case, we're going to be doing the same steps into finding the equation of a tangent line. we're going to find that first derivative. We're going to use, again, we're going to plug in the x value there to find the slope, and then we'll use the point slope formula with the point that's given and the slope, and we'll be able to solve for y from there to get the equation of our tangent line. Let's go through each process. First and foremost, let's find the derivative of this. Derivative of this is we keep the exponent the same, e to the minus x squared. Take the derivative of minus x squared, which is minus 2x. That's your derivative. Okay. Now in this case here, we are given a point here of 3 comma 1 over e to the 9th. I'm not really going to care too much about 1 over e to the 9th until the end, but I do care about the 3. That is more important than what I'm doing in this case. So I'm going to do f prime of 3. Again, from the point here of 3 comma 1 over e to the 9th. So if I plug in 3, I'm going to get e to the minus 3 quantity squared times negative 2 times 3. Now what we get here is we get e, 3 squared is 9, so we get e to the minus 9 here. Notice that's why I put the 3 here in parentheses. That negative is separate than that of the 3. Okay, so just pointing that out there. That's why I put the 3 in parentheses in that very specific way. I get negative 2 times 3, which is negative 6. So putting this together here, making it look nicer, I get minus 6 e to the minus 9. Okay. Or, if you wanted to, you can always put this as, you could always write this as negative 6 over e to the 9th power. Either way. That's, either way you write it, that's what it's going to be. Okay. Now, let's go ahead and use the point that's given here. So the point that's given here is 3 comma 1 over e to the 9th. We're going to use that point slope formula that we talked about from before. Let's not forget the point slope formula here was y minus y1 equals m times x minus x1. Remember, the whole purpose of doing this first step here, I guess we'll call this step 1, is this is the slope, m. Okay, so this negative 6 over e to the 9th, or negative 6 e to the minus 9, whichever way you want to write it, is going to be the slope that we have. And this 3 here is going to be our x1, and this 1 over e to the 9th will be our y1. And so we're just going to plug it into those 3 specific spots and solve for y. We have y minus 1 over e to the 9th equals negative 6 over e to the 9th times x minus 3. Okay, so let's clean things up a little bit. A little ugly. We get y minus 1 over e to the 9th equals negative 6 over e to the 9th. X minus 3. So here we get negative 6 over e to the 9th. X plus 18 over e to the 9th. And then finally, we go ahead and add by 1 over e to the 9th on both sides. Again, you just take it like a fraction. You have the same common denominator here of e to the 9th. So you could just add 18 and the 1 together there straight up. And you will get y is equal to negative 6 over e to the 9th times x plus 19 over e to the 9th. And that will be our final answer for our problem. Are there any questions about that? Let's try out the answer here, by the way. Oh, that X should be on the side there. All right. So if we try it out here. All right, and you notice that we got the correct answer here. So it looks pretty ugly, I ain't gonna lie, but it is the correct answer. All right. Any question? Yoga, I already asked that. Questions about that. That's fine. Okay. All right. That's true. Okay. So, all right. So I want to take a look here at the next three. I want to take a look here at one of the next three problems here. This is stuff that we talked about here earlier on in chapter 4. We talked about increasing and decreasing intervals. We talked about inflection points, and we also talked about absolute extrema. So again, each one of them has their own process, again using first or second derivatives. Okay. Now I want to do one of these problems here because I want to give yourself a little bit of practice with the other two. So let me know which one you would like me to do. So you guys get the pick here of 11, 12, or 13. So in this case here, 11 is increasing, decreasing intervals. 12 is inflection points, so that's the stuff with concavity. And then 13 here is the absolute extrema here. So they both are very unique in their, of course, concepts here. The one's not necessarily harder than the other, it just depends on which one you would like me to do. That'll be the next example here. So which one would you like me to do? 11, 12, or 13? All right, Elizabeth says number 12. All right, Emma says number 12. All right, I just need one more vote, and then I'll do number 12. All right, so number 12. There we go. All right, let's do number 12. Let's see what we're working with here. I don't know, but we'll find out, right? Okay. Actually, I'll put this here. All right, so the next problem here will be number 12 from our homework. All right, so in this case here, they tell us to find the inflection points of 5e to the minus x squared. Okay, now in order for us to go ahead and do that here specifically, what we need to do here first is we need to go ahead and solve for the first and second derivatives of this function. So let's take a look at both of them. So the first derivative here, again, nothing too fancy going on here for the first derivative. 5 stays the same. The e to the minus x squared stays the same. But we take, of course, with the chain rule here, we have to take the derivative of the exponent, which is negative 2x. So putting this together here is actually going to be fairly helpful. Okay, this will make things significantly easier to find the second derivative. That's going to be minus 10x e to the minus x squared. Okay, so that's our first derivative done and done. Okay, now we need to find the second derivative here. However, in this instance, the second derivative here is going to be a little bit tougher than the first. As you can see, though, we have one function multiplied by another function. So what we're going to do here in this instance is go ahead and apply the product rule for this particular problem. Again, this minus 10x will be our f, and then this e to the minus x squared will be our g. Let's find the, again, f prime g plus g prime f is what we're after here. So derivative of this f here is going to be minus 10. Derivative of that g is going to be, again, the same derivative we have here. We have e to the minus x squared. Keep that the same. Take the derivative of minus x squared, which is minus 2x. Get minus 2x, e to the minus x squared. All right. We're going to need to put these pieces together here. So let's do f prime g first. So f prime g, so we get negative 10, e to the minus x squared. All right. With negative 10, that's f prime, and g, which is e to the negative x squared. All right, here we have plus g prime, which is this, negative 2x, e to the negative x squared, times f, which is negative 10x, okay. Okay, so cleaning this up a little bit, let's take a look at the overall guy here. We have negative 10 e to the minus x squared. Minus 2 times minus 10 is plus 20. So plus 20x specifically. All right, e to the minus x squared. Oh, sorry. Excuse me. Minus 20x squared. Pardon me about that. Because we have x times x here. Okay. All right. But before we move forward here, I know finding the second derivative here is a little tough. So, any questions about the first and second derivatives here before we move forward? Here we have negative 10x there as f for our guy here. Remember that if we just take x here, remember that if we have, say, 2x, the derivative of that is 2. It just drops out. The x just drops out. Again, same deal as like if you had, another way to write 2x is like 2x to the first, right? So you'd bring the 1 out using the power rule here. So you technically have, again, 2 times 1 times x to the 1 minus 1. So you have 2 times x to the 0. But anything to the 0 power is automatically 1. That just leaves you with 2, for example. So again, negative 10x works exactly the same way. Any other questions? All right. Nick, are you doing okay? I hope you've been able to keep up here. Hopefully it's a little bit hopefully it's not too bad. Just let me know. Hanging in there. Okay, good. All right. Now the next part here, that I want to talk about is we need to set this equal to 0 to solve for x. Okay. So if we're gonna do this right, we're gonna find our values here to see where we do our intervals and all that. We need to set this equal to 0. Okay. Now, in order to do this out, what we're gonna do here will seem a little strange, but it works. we're going to do a little bit of factoring here, okay? So what does this factor to, this guy right here? So notice that there is a 10 in each of them, okay? So we could take out, say, for example, a minus 10 in each of them, or a positive 10. Let's just keep it simple. For you guys, let's just keep it simple and take out a positive 10. And also in each term here is this e to the minus x squared. That's also in each term here. Now if we take out a 10 e to the minus x squared, let's see what we have left over. Well, we have a minus 1 here, because that's minus 10. And here we take 20 divided by 10, which is 2, with the x squared here. So we get plus 2x squared equals 0. Does everybody see where I came up with that? Are there any questions about that? Everybody okay with that factoring? I hope so. Like I need to navigate through this next part here very carefully. So it's not hard to explain, but it can trip you up rather easily if you're not careful. So I want to be sure you guys understand. All right. So the next thing that I'm going to talk about here is what happens after that. We're going to set both of these equal to 0. We have 10e to the minus x squared is equal to 0. And we have negative 1 plus 2x squared equals 0. Now, as for the first part here, get rid of all this junk here. As for the first part here of 10 at e to the minus x squared is equal to 0, as ugly as that looks, we actually are going to luck out here just a little bit with what the value is for x. Because in this case here, there is actually no value for x that makes this 0. Remember, anything we do for exponents will never make that 0. So you can pretty much take it to the bank that no x value is going to exist that's going to make that 0 at the end of the day. Okay, so you can just throw that away, and that just leaves us with minus 1 plus 2x squared equals 0. Now in that case, we do have values here. Do a little bit of algebra. We have 2x squared is equal to 1. I can draw equal signs. We're going to go ahead and divide by 2. We'll have x squared is equal to a half. Take the square root of both sides. So we're going to get two answers for x. We're going to get plus or minus. Now, just before I write this down here, remember that square root of 1/2 is the square root of 1 over the square root of 2. Square root of 1 is just 1. Square root of 2 you can't do much with, but one thing that will be expected for you to do here for these problems, especially with square roots in the denominator, must rationalize the denominator here. So I'm going to multiply this by square root of 2 and square root of 2. So what we get here is we get, specifically, we get square root of 2 over 2. And we're going to get the plus or minus version of that. Okay. I'm just pointing that out here. In this instance, we get plus or minus square root of 2 over 2. Basically, try entering that answer with the square root of 2 on the bottom, and it usually tells you it's wrong. So have to rationalize the denominator there, otherwise the homework hates that. So can't say I'm a big fan either. All right. Okay. Go ahead and make our chart here. Again, if you need to write out your number line, you have negative infinity, positive infinity, negative root 2 over 2, positive root 2 over 2. So we have three intervals here. We have negative infinity to negative root 2 over 2. Okay. We have negative root 2 over 2 to positive root 2 over 2. And then finally we have root 2 over 2, comma, infinity. All right. Take a test point here in each one. So as a decimal here, you know what? I'll pick some silly values. It's fine. I could pick like -7 for this. I could pick 0 for this. And I could pick +7 for this. I know that those are big. So, all right. So I'll pick three values that are, again, in each one of those intervals is what we're going to do next. And we're just going to see if they're positive or negative to test for concavity. Okay, so in this instance, again, though, remember, you will need to plug this into, once again, we're going to plug that into the second derivative, okay? So we need to plug it into, where is it here? Yeah, we need to plug it into the second derivative that we found here earlier, which is this guy right here on the very top. Or you can plug it into the factored version as well. Okay. So if I try -7, for example, I'm going to get a... Yeah, okay. So if I try -7, you can try it in this function here. 10e to the -x squared is always positive. It doesn't matter what number you plug in there. If you apply -7, you get a positive number on the inside of parentheses. So a positive times a positive will be a positive. Again, like we mentioned here, we don't care what the number is. We just want to know the sign of the number. 0 is going to be negative inside the parentheses and positive on the outside. So this will be negative. And then +7 will be like its counterpart, -7. And that'll be positive. Okay, so now what we have proven is that negative root 2 over 2 and positive root 2 over 2 are indeed inflection points here for this particular problem. All right, so we did a lot of work there in order to finally get down to our final result here, which took us a while to get to. But now that we found our two x values here, they do want specifically here, go ahead and maneuver this over, they want a xy coordinate here. So what they would like you to put in is they would just like you to plop in negative root 2 over 2 inside the original function. So you're going to get f of negative root 2 over 2. That's going to be 5e to the minus negative root 2 over 2 quantity squared. You can clean this up a little bit, and you will end up with 5e to, this is, what is this? 2 over 4, so 1/2. Okay, so 5e to the minus 1/2. That's what we get there for that. And so we get, let's get here, get negative 2 over 2, comma, 5e to the negative 1/2. And if you try The other one here. Oh, right. This square root of 2 over 2, comma, and you will actually end up with the same y value here, so I just don't want to repeat the steps again. So, all right, so this should be our two inflection points here. So let's try it out, and we'll see if it's correct. And that is correct. So as you can see here, those are indeed the correct inflection points. So that one there is a pretty involved problem, so it's probably good that you selected that one. That one's more involved than probably the other two. But that is the answer for number 12. A lot of manipulation, but just take it slow for that one in particular, okay? Any questions about that? Let me know if you have questions. I know you guys are probably still writing stuff down. So okay. Good stuff. All right. That's hard. Emma, Nick, Elizabeth, any questions? Nope. Yep. All right. Okay, so let's take a look here at 14, 15, 16 here. So I will let you guys choose once again if you want me to do 14, 15, or 16. So 14, 15, or 16 here. Just let me know which one you would like me to do. And we could do one of those word problems there. Oh, we got some different takes here. So 16 and 15. Okay, so one vote for each of those. We'll have Emma will like 16. I'm not sure what Elizabeth would want, but we'll see. Elizabeth, which Elizabeth wants 16. Okay, so we'll do 16 here by democratic vote. All right. The price of perfume. So the monthly demand for a certain brand of perfume is given by the demand equation P is equal to 100E the minus 0.0003 x plus 75, where P denotes the retail unit price in dollars per bottle, and X denotes the quantity in 1 ounce bottles demanded. Letter A. Find the rate of change of the price per bottle in dollars when X is equal to 1,000 and X is equal to 2,000. So, of course, a two-part problem here, but actually, this one here isn't as bad as it may seem. Reason why here specifically is because of the fact that it's just asking you here for rate of change. When it asks you for something like rate of change or how fast something is going, for example, like number 15 here, it asks how fast it's going, or rate of change. In effect, that's just asking you to find the first derivative and then plug in the numbers. All right, so just as a friendly reminder here, again, remember rate of change or fast or whatever. Rate of change is equivalent to, say, the first derivative here. Let's find that first derivative. In this case here, the derivative is going to be, let's see here. We have, we're going to keep that E the same. That power. Let me check. Is that, hang on a second, sorry. You're not having a tough time reading it. There we go. Okay, so 1, 2, yeah, 1, 2, 3 zeros, okay. All right, and then we're going to multiply that by the derivative of the exponent here, which is negative 0.0003. The 75 will drop out because, again, the 75 doesn't have, again, the derivative of 75 is 0. So if we go ahead and multiply 100 times 0.00003, triple 3. So here, if we just clean this up a little bit, we get negative 0.03 e to the minus 0.0003 x. Okay. So all we want to do here specifically now is just plug in 1,000 in for x in this first derivative and 2,000 in for x here. Put that on the calculator, see what we get. We get negative 0.03. Now to get e to show up on your calculator here, okay, be sure to go ahead and enter this in appropriately. And you just have to hit the second key and the ln key, the natural log key, and you'll get e to show up on your calculator. Then you'll put negative 0.0003 times 1,000. Okay, so with x being equal to 1,000, we get negative 0.022. All right, let me see how many decimal places we want here. 4 decimal places. Okay, they want 4 decimal places, so put another 2 there. All right. And then x is equal to 2,000. Let's, let's repeat the same thing. Negative 0.03. Second and natural log. Negative 0.0003 times 2,000. So here we get x, we get equal to negative 0.0165. Okay, so rounding 4 decimal places, that's what we should have. So let's take a look here at this and see what we get. So let's see if we got it right. So negative 0.0222. This one here, negative 0.65. Test it out. But we'll do letter B here in just a second. So just checking the tougher of the two parts. And as you can see there, that's correct. Okay, so we got that. Got those first two parts there for part A. Got part A here correct completely. And now it asks us for the second part here. The second part is by far the easier of the two parts, at least for this question. What is the price per bottle in dollars when X is 1,000, when X is 2,000? So all they want us to do here for letter B is just plug in 1,000 and 2,000 into the original function and then seeing what value you get. So there's not much you're doing. You're not doing derivatives for the second part. It's just like, okay, plug in the original function. Tell me what you find out for the price. Like, all right, fine. So we get 100 e to the minus 0.0003 times 1,000. And we'll add that to the 75 in the original OG function. So let's see what we get here when we plug it in the calculator. 100 second natural log. Put some parentheses here. Be careful. Make sure to put parentheses there. So again, you section that off appropriately. If you have an old school calculator, it'll have parentheses to start with when you hit second and natural log. And then we'll add 75 to that. We get 149.08. I think they want us to have to the nearest cent. Let me take a look. They want the nearest cent? And your answer to the nearest cent. Okay, they did. Okay, so 49 points. Okay, so and we repeat this process here with 2,000. You could take a little shortcut here. You can hit second and enter. It'll actually bring up your previous entry. And if I just want to put 2,000 there, I can do that. So this is for 1,000. We get 129.88. Now let's check it out. All right, and those are correct. Just a simple plug and chug type of problem is what they asked us for in the second part. Okay, great. Questions about number 16? That will take care of number 16. Again, part A is the tough part because you got to do the derivative. Once you get past that, the second part there is pretty standard. All right. Lewen, Elizabeth, Nick, do you have any questions? That is effectively the end of this section here for section 5.4. So just going to point that out here. Although we only answered one question on the handout, there's just a lot to do with that one question, a lot of applications and stuff. So we got it done. So that's good. Got exactly what I wanted to get done. Don't think so? Okay. Well, a lot of information here today, but that's okay. I want to thank all of you for coming on out here to the stream today. Thank you so much, all of you. I know, Nick, you're a little bit late, but don't worry about it. I'm glad you just came out, man. glad you came out. I'm glad that you're willing to put in the time and the effort and everything like that. So thank you for coming out. I appreciate that very much. Thank you very much, Emma. Thank you very much, Elizabeth. Thank you very much, Lee Wed. Thank you very much for anybody else who decided to stop on by and kind of lurking around. I really appreciate it. Again, you guys were on a very good pace here. We're doing good. We're doing good. Again, the next test is over chapters 4 and 5, so I got to be able to. I'm gonna have to make up the test regarding that and post that online. That'll be a me problem, not a you problem. That'll be either posted tomorrow or over the weekend. That is the plan here. We're almost done with chapter 5 here, so we're very close to being done with chapter 5. So we're getting down to the very final throes of that. So that will take care of for today, and we'll continue moving forward here with chapter 5 for next time, okay? We will see you all tomorrow here, same time, same place. I'm looking outside there. I hope everybody has a absolutely wonderful evening. All right, please, everybody, take care of yourselves, and we will see you then. All right, have yourself a wonderful, wonderful evening again. And as always, stay safe, stay healthy, but most importantly, stay sane. All right, take care of yourselves, everybody. Have a great one. All right, see you later. Bye. Ah, see you, Elizabeth. See you, everybody.